We're going to look at inverse trig functions. In order for be a trig function, it has to be continuous, right? So it has to be continuous and it has to pass the vertical line test. So if we look at sine, sine of 0 is 0, sine of pi is 0, and sine of 2 pi is 0. So we can do the vertical line test through here, and we can see that it passes the vertical line test. But when we graph the inverse, function, we're flipping our x's, which are really our angles. That's pi, 0, pi halves, those kind of things. And then our y values is the ratio of the sides, right? So those are just numbers, go up to 1, and go down to -1, right? So that's going to flip. Our y's are going to become our angles, right? And negative angle. And through here, our x's are now going to become our numbers, 1, or -1 and 1. But in order for this to be 1 to 1, right? If I switch these, in order for it to be 1 to 1, the horizontal line test would tell me if the inverse is a function. So if I do the horizontal line test, this fails the horizontal line test. So its inverse is not a function. So that means I just need to restrict the domain. So if I restrict the domain from 0 to, say, pi halves, then I can go ahead, or actually restrict it from pi halves to 3 pi halves. Then this graph goes from right here down to right here. It does pass the horizontal line test. So it does pass the horizontal line test through here. So that's what we're going to do here. We're going to restrict our domain. And then so when we take the inverse of this, so I'll have pi halves, or even negative pi halves. I can go this way with it. So this right here would be negative pi halves, right, to pi halves. So negative pi halves to pi halves, right, because these are my x's, and now they're going to be my y's. And I go from down at -1, so my first x is -1, to +1. So it's going to look something like this. It's still going to have that kind of general curve to it, that cubic looking curve. Maybe more like that. Okay, so there it does pass the inverse. Sine inverse does pass, so it is a function. Okay, but you have to restrict the domain of sine in order for its inverse to be a function. Okay, so, and then we can switch between inverse and non-inverse. Like if I have y equals sine inverse of, say, x, to switch that back and forth, just the y's and the x's, they change places, right? X equals sine inverse of y. And again, my x's would have to be restricted on some sort of domain, right? So from negative pi halves to pi halves in order for that to be a function, right? So we can switch the x and y just like any other inverse, and then we use the term inverse function, right? That's how we write inverses. All right, so if you remember pre-cal, remember finding inverses just going backwards, it's actually finding the angle. So when I'm trying to find the sine inverse of 1/2, I'm trying to ask, what is the angle that gives me 1/2 as an answer? So sine of what angle equals 1/2, right? So here, sine inverse of 1/2 equals, say, x. Then this switches places, right? So this, or I guess I could use theta, right? This switches places. These two switch places because they're inverses, right? And so we're answering this question. Well, what angle gives me 1/2? Well, that's going to be a y value is pi 6th. So pi 6, so theta equals pi 6. And then this one, so that's on the unit circle, right? This one is not on the unit circle. So there we can think, another word for inverse sine. Inverse sine is arc sine. right? Or arctangent, inverse of tangent, and so forth. So if I'm not on the unit circle as this one is, then what I can do is I could draw a triangle. So this is saying some angle of sine produces a 1/3. Well, sine is opposite over hypotenuse, right? So that's 1 over 3. So then I could use Pythagorean theorem. 3 squared minus 1 squared equals this side squared. So we can go 9 minus 1 is 8. Square root of 8 is 2 root 2. So this side is 2 root 2. So once I have 2 root 2 there, now I can go ahead and answer what tangent. So tangent of this same angle. What's tangent of this same angle? Well, tangent of that angle is opposite over adjacent. So that answer is 1 over 2 root 2. And we can go ahead and leave it just like that. So that's what tangent of theta equals 1 over 2 root 2. So whenever you think about arc sine or inverse sine, it's asking for what is the angle. And if you're not on the unit circle, then you can draw your triangle, label that angle, and then see what the outside is asking. And then here are a couple of things that are true. So sine of sine inverse of x is always going to equal x. And then sine inverse of sine x is also going to equal x, right? Because this is asking for what is the angle, and this is saying go ahead and perform, find the sides. So it's going to get you back to that. All right, let's go ahead and look at the derivative of sine inverse of x. Or, yeah, let's go ahead and look at this one first. Or really, we could do this just as a u, right? Because really, you're not just always going to find the derivative of sine inverse of x, right? So the sine inverse of x basically is of an angle. So sine inverse of an angle is going to be this, 1 over square root of 1 minus x squared, okay? Now the problem is if this is not x, so if that was a sine inverse of x squared, that's going to look different, right? Because you got to do chain rule. So you got to take the derivative of sine inverse of x, and then you got to times that by the derivative of the inside, right? The derivative, well, you got to do, I guess you got to do u, right? Du with a u here, and then you take the derivative of u, right? So how this is always going to be is this is just going to switch to 1 over square root of 1 minus u times du. Or not, sorry, not du. D, or we can just say the derivative of u. Let's just use prime, u prime, right? So this is always just going to be u prime over 1 square, sorry, u prime over square root of 1 minus u. Okay, so that's how these are always going to turn out. So here's an example. Right, so if you have sine inverse of something other than just x, I'm going to take the derivative of that inside, which is just 2x, and I'll take it over the square root of 1 minus whatever that x is. So x squared minus 1. And then I can simplify this, right? Square root of 1 minus, that's going to become a negative x squared. That's going to become a positive 1. So that's going to cancel out. Or sorry, that's not going to cancel out because this is actually being squared. Because, no, we're fine. Okay, so those are going to cancel out. And then, so I just get, they're not going to cancel out, sorry, because this right here is supposed to be a u squared. That's supposed to be a u squared, so that means that's being squared. So that would be x to the 4th minus 2x squared plus 1. So those ones will cancel out because when I distribute that negative, I'll get a negative x to the 4th plus 2x squared under the square root, and I can't simplify that more, so my answer to this is, or the derivative of that is 2x over the square root of negative x to the fourth plus 2x squared. Sorry about that. Totally messed up that. There's that. That is being, that u right here is being squared. Okay. All right. All right, let's go ahead and take a look at cosine. We can do the same thing with cosine. We can restrict its domain so that's inverse as a function. And so we can take this inverse function, rewrite it, and that also means arc cosine. This means the same thing. You can switch the x's and y's, right? And those are switched back and forth, right? So, and then the derivative of that, oh, and this is, yeah, the derivative of that cosine inverse of x is equal to negative 1 over square root of 1 minus x squared. So that means when I do the u, anything other than x, negative u prime over square root of 1 minus u squared. Don't forget that squared. Okay. All right. I guess this would be an x probably. Taking the derivative. Okay. And then this is also true. Cosine inverse of cosine of x equals x. Cosine inverse. And then cosine cosine of cosine inverse of x also equals x. Same thing as sine. All right, so let's go ahead and look at tangent. So there's some different things that you can do here. I'll just give you the derivative of tangent. I think on page 457 kind of explains how you kind of get there. The tan inverse, the derivative of the tan inverse of an angle is 1 over 1 plus x squared. So I don't really want to go into the detail, and you can find all the rest on page 457. You can find all the other derivatives of the inverse functions, all 6 of them. So they'll be located on that page. But if you have any questions on the derivatives, just let me know. Let's go ahead and get to the integrals. So the integrals, there's a few of them here, mostly for sine and for tangent, and then some different looks. But because we're going backwards from the derivative, that means we're going to be taking the integrals of the derivative of inverse sine, right? So the derivative of inverse sine was 1 over square root of 1 minus x squared. Don't forget the squared, right? So that means when we take the integral of this, we're going to get our sine inverse. And then if we're taking the indefinite integral, then it's going to be, we have to add our c at the end. Okay, then the integral, like I said, tangent was 1 over x squared plus 1. So when we take the integral of that answer, we're going to get the inverse of tangent, and then we add c. And then if you get into more complicated ones, anything that kind of looks like tangent, where you have some sort of x squared on bottom here, and then you have some number that's being squared, you can write it as, when you take the integral of that, you can rewrite it as a form of tangent. So it's 1 over a tan inverse of x over a, and then we add our c at the end. So that's kind of a form of tan inverse. Okay, so those are your integrals, and you can work on some problems. If you have any questions, let me know.